Mitochondrial production of usable energy in the form of ATP is how you produce everything in your body, how you maintain it, repair it, and put it where it belongs. Mitochondria need to do all this for themselves, and if you're losing your mitochondrial function, you're trapped in a vicious cycle of mitochondrial decline that's driving down the ability to maintain and repair everything else in your body, making it clear that mitochondrial dysfunction is the process of aging.
The following content is not medical advice and is for educational purposes only.
Mitochondria are responsible for protection against disease. They're responsible for abundance, adaptability, and resilience throughout your life. They're responsible for physical, mental, and cognitive performance. And reaching into the future, they're responsible for your longevity. To be more specific about what this means for you, this means everything from beautiful hair, skin, and nails, building muscle, losing fat, and performing athletically, to sexual appetite and performance, to fertility. And it allows you to beat fatigue, depression, anxiety, OCD, to prevent diabetes, cardiovascular disease, cancer, and neurological disease. So how do mitochondria do this? And the answer is that mitochondria serve to convert the energy in the food that we eat into usable energy for our cells in the form of ATP. And we can think about what this means by thinking about in our daily life and in society, what does energy production enable? So we have power plants and refineries, and they convert raw materials like fossil fuels, sun, wind, and water into usable fuels like gasoline and electricity. What do we do with those? We produce everything in our lives. We maintain it, we repair it, we transport and distribute it. And this is what allows us to have civilization, and as a civilization, what allows us to have prosperity. We are doing the same things at a different scale within every cell of our body with the usable energy that mitochondria make when they convert food to ATP. Every single thing in our body is produced with that energy. That energy is what allows us to maintain and repair it, to transport it and distribute it, to make those things go where they belong, and that's what produces health and longevity. So let's think about what each of these things means for our health outcomes. If you think about what it means for mitochondrial dysfunction to cause a loss of the energy needed to transport and distribute things, you can liken it to the same thing in your daily life. So for example, when you clean your room, you invest energy in putting things where they belong because they go where they belong, you're happy with it, you're comfortable in it, and it's easy to find things and it's easy to be productive. But if you don't invest that energy, what do you get? Your room is a mess. And so beneath the surface, there's a causal pattern, which is you are not investing the energy. And what you see as a result of that is that you've got a messy room. In your body, you don't know the biochemistry and cellular biology of it, but what it might look like at a cellular level is you are supposed to have nutrients that have a gradient across a membrane, and instead of being in a higher concentration over here and a lower concentration over here, they're all mixed together. Now, what would you see as a result of that in your health? Intuitively, you can think about it as you're all backwards and mixed up. So for example, if you're wired and tired, if you are skinny fat, if you are shaped like an egg or an apple instead of having a chiseled physique, if you have fatigue coexisting with anxiety, if your muscles are weak on the one hand, but they're also tense on the other hand, if you've just got a lot of muscular tension, but you're not that strong, you've got a problem. Your muscles are contracting at all the wrong times and not contracting with power when they should. Similarly, you could have weak muscles combined with twitches or combined with tremors. Those are different examples of how your muscles could be contracting when they're not supposed to and not contracting when they're supposed to. You could be losing muscle and bone, the things you're supposed to build up, but then you could also be growing cancer or atherosclerotic plaque, things that you don't want in your body. So you're investing your anabolic energy in growing things you don't want, and you aren't investing it in keeping the mass that you do want. These are all examples of paradoxes, of things coexisting that shouldn't, of things being all mixed up and things backwards. That is the surface result that you see when at your cellular level you lack the mitochondrial energy production needed to put things in their proper place. Now think about what would happen if you were not using mitochondrial energy production for the maintenance and repair of the things in your body. You are going to see things like you get sick, but then instead of fully recovering from that sickness, you have leftover health problems as a result of a failure to repair the tissues that were damaged. You have graying and loss of hair. You have wrinkles and spots in the skin, cardiovascular damage, genetic damage that contributes to cancer on the one hand or infertility on the other, and neurological damage that leads to things like dementia and movement disorders as you age. And then what would happen if your energy was not being invested in producing things? You would see things like difficulty gaining muscle because you can't synthesize the tissue that well. Poor wound healing because now you've got to repair something that was broken and you need to synthesize new tissue, not just repair the things that had been broken, and you're not able to synthesize the new tissue. Inability to synthesize fetal tissues during pregnancy, that can lead to a miscarriage instead of a healthy pregnancy carried to term. And failure to support your immune function. Why? Because when you are about to get sick, in order to defend yourself against that sickness, what you need is a massive production of immune cells. They have to divide into many, many, many cells very, very rapidly. And if they can't expand fast enough by producing new proteins, producing new cell membranes and dividing, then you are not going to have the army of immune cells that you need to fight off that coming illness, and you're going to get really sick. But then that can feed back to, if you can't repair the tissues after you get sick, now you're in for a post-infectious chronic illness. Mitochondrial dysfunction drives aging, and you have the power to stop it in its tracks. Consider this. If mitochondria produce ATP, but ATP is what is needed to produce things, maintain them, repair them, and put them where they belong, then ATP is also needed to produce everything in the mitochondria, to repair it, maintain it, put it where it belongs. And that means that mitochondria are fueling their own survival. Now, what happens even if you have the most perfect mitochondria in the world? You are genetically blessed. What's going to happen if you have one day of bad nutrition or bad lifestyle? If you get sick or you get injured or you have a surgery or something happens where now for that day, your mitochondria had been producing the perfect amount of energy, but now you have a deficit. Well, that deficit might leak back in the form of ATP was diverted to protect you against whatever you had to deal with, and now there's a little bit less to support mitochondrial maintenance and repair, and your mitochondria got a little bit worse. But if they got a little bit worse, what's going to happen as a result of that? They're going to make a little bit less ATP. And then that's going to make you more likely to get sick the next time, even if it's just 1% more likely. Now you've got another deficit. Your mitochondria get a little bit worse. Now maybe you're 2 or 3% more likely to get sick, or 2 or 3% more likely to get injured. And this just continues in a vicious cycle on throughout the years. And as a result of that, you can see in the figure on the bottom of the screen that mitochondrial function declines with age on average about 1% per year. This is taken from skeletal muscle. This paper that's cited at the bottom has a number of different measures of mitochondrial function. This graph is showing you one of them, but it's representative of what they all show, which is that there's just a downward trajectory starting around age 18 through the lifespan where the mitochondrial function is just going down. And that means less ATP, less mitochondrial support, less ATP for everything else. Now, the good news is if you look at this graph, on the one hand, you've got this downward slope. On the other hand, you've got a lot of variation at any given age, 20, even say, in the 60s and 70s. Although there's a trend, age only explains about 25% of your mitochondrial function. That means that 75% is up to you. And you have the power to optimize that 75% of your mitochondrial function through proper diet, exercise, supplements, and mitochondrial testing to figure out what your unique needs are. Not focusing on mitochondrial function first is always a mistake, and I'm going to give you 3 examples of this. Let's say we're talking about depression. Depression starts with your mitochondria. How do we know that? The most powerful geographic determinant of the rate of depression and suicide in any given location is altitude. Altitude means less oxygen available. What does oxygen do in your body? It goes into your mitochondria and it facilitates the conversion of food to ATP. So fundamentally, on a geographic level, what we're seeing is that depression is primarily correlated with a lower ability for mitochondria to convert food to ATP. And this is probably explained by the fact that that energy is needed for stress resilience. Now, if you look at clinical trials of nutritional supplements for depression, one of the most important of those is SAMe. This compound, also known as S-adenosyl methionine, is support for the methylation pathway. And the reason that methylation is important to depression is that methylation is helping provide mental flexibility. We know from functional MRI studies that if there is less methylation in the brain, what happens as a result of that is that when people are exposed to negative images, their emotional center in their amygdala is far more likely to activate with what's called in science a negative emotional valence, which basically means they get emotionally disturbed by what they see. And you can extrapolate from that study and say they're going to get more emotionally disturbed by the things that happen in their life, by the stresses that they're exposed to, by the interactions that they have with other people, by their own thoughts. And the reason that the emotional centers light up more when you have lower methylation is because methylation is altering the stickiness of your brain. It's lowering the stickiness, making it more flexible. And when your brain is flexible enough, you can have a negative emotion or thought that comes through and you just let it go. And so it doesn't bother you. If it gets caught in that net because your brain is so sticky, now you have a greater chance to get emotionally disturbed. But you don't have to. You can fight that off with your prefrontal cortex, where you are using your executive control. And you can start to feel that negative emotion, but you can invest energy in fighting it off and saying, no, I will not listen to that negative thought. I refuse to listen to that angry emotion or that sad emotion or that depressing way of thinking. And you can burst it out of your mind. Now you can see an interplay with this, and you can start to see where just not having enough total energy in your brain is actually going to interfere with that. Because if you're mentally too sticky and the negative thoughts get stuck in your brain a lot, and you have to then exercise power, mental cognitive power in fighting that off, if you don't have the energy reserves, you're not going to be able to do it. And one of the things that we see in people with low methylation in their brain is that they get mentally exhausted because they're investing what seems like all the energy they have in their brain in fighting off these negative thoughts. And if they can't do it, if they give up too easily, those negative thoughts overcome them, and that can then interact and synergize to produce a chronic problem of depression. Now, if we look at the methylation pathway, one of the things that we'll see is how do you get SAMe when you're not taking it as a supplement? You have an amino acid called methionine, And every time that methionine contributes to methylation, it converts into an amino acid called homocysteine. And in order to recycle that, you need a compound called methylfolate. And that famous MTHFR gene, which many people have, is an impairment in the ability to make methylfolate. But you don't just need MTHFR to make methylfolate. What else do you need? You need mitochondrial conversion of food to ATP to turn the folate into methylfolate. If you don't do that, no matter how good your MTHFR is, if you don't have mitochondrial ATP production, you aren't going to make any methylfolate. If you don't make methylfolate, you're not going to be able to convert homocysteine to methionine. Now, let's say you do have methionine. There are multiple ways to skin a cat, right? You could just eat a steak and you'll get plenty of methionine. But is that going to support methylation if you don't have mitochondrial ATP production? Absolutely not, because now you need your mitochondria to convert food to ATP in order to convert methionine to S-adenylyl methionine, or SAMe. So what are we seeing when clinical studies are showing that supplementing with SAMe outperforms even SSRIs and other antidepressant drugs, or at least is just as good as them in battling depression? What we're seeing is that the product of the methylation pathway that required at least one use of mitochondrial ATP production, if not two, to make, is helping make people more mentally flexible so they don't have to invest as much brain ATP in fighting off the negative thoughts that lead to depression. The problem with just willy-nilly supplementing with SAMe, though, is that although it is profoundly effective on average, it is not without its problems. It has an extremely high rate of gastrointestinal distress, and there are some people that develop other problems with it, like new onset mania. So what we really want to be doing in order to battle depression is optimize mitochondrial conversion of food to ATP so that you have just enough SAMe that you need, and you don't have to take high doses to disturb your gastrointestinal function, because you're actually making it in your brain, so it's not causing any problems, and your brain is not going to overmake it and cause new onset mania. Your brain with optimized mitochondrial function is going to make exactly how much you need. Instead of this, we've ignored all of this, and we've come to using SSRIs as the first-line treatment of depression. Well, what's the problem with this? The problem with this is that SSRIs do outperform placebo, but if you look at the numbers, about 75% of the impact of an SSRI is the placebo effect. Then that's fine. You could say the same thing about nutrients as well, because placebo effects are very large for any treatment of depression. The problem is, though, if you look at the side effects, you see that half of people who use SSRIs report emotional blunting. This means that they're not just blunting against depressing thoughts, they're also being blunted against their happy thoughts, meaning they just don't feel as much overall. They don't feel as happy. They don't feel as sad. They're just put into the middle because they just don't feel as much. So a lot of people look at that and they say, well, are SSRIs really doing anything else? Because the rate of emotional blunting is actually higher than the rate at which the genuine non-placebo biochemical effects of the drug help depression. They're causing more emotional blunting than they are actually fixing depression. The only reason that it doesn't look like that is because people aren't subtracting out the placebo effect from the effect of the drug that is seen in clinical trials. That's not the whole of it, not by a long shot. Half of people who use SSRIs don't only experience emotional blunting, they also experience sexual dysfunction. A lot of people who experience emotional blunting and sexual dysfunction say, hey, I'm not sure if this is better than the depression that I had before I was on the drug, and so they try to go off of it. The problem is that clinical trials have convinced physicians that anyone can go off SSRIs. They might just need a 6-week taper, and they might experience some withdrawal symptoms, but it's not a big deal, and they'll be over in 2 to 3 weeks. Well, that's true if you're looking at someone who's been on SSRIs for 8 to 12 weeks, like almost all of the clinical trials are done. But in the real world, people are on SSRIs for 1, 2, 3, 5, 8 years before they go off. And there are 0 clinical trials that are done longer than a year. 0 that are done for 5 to 8 years. And what you see is that 38% of people who try to go off SSRIs cannot go off them because the withdrawal symptoms, or the discontinuation syndrome as they call it in the literature, prevents them from being able to go off the drug. They have to go back. And so they go back on it, or they yo-yo between it because they can't stay on it, but they can't go off of it. The people who power through that and go off anyway, despite the problems, sometimes report years of new onset problems lasting up to 14 years. And these new onset problems are not just a relapse of depression, not by a long shot. They're problems that these people never had before. Problems like twitching, cramps, paresthesia, neuropathy. These are, tingling in your hands and feet, or feeling like something's crawling on your skin, just feeling things that aren't there. Hallucinations, amnesia, and brain zaps. Brain zaps are very widely reported, very little looked at in the literature, but they're often felt like a shock in the head. Sometimes people say they can see them or hear them. Sometimes people describe them in very odd terms, like the video of their brain is buffering and things like that. So going off SSRIs is causing people problems, new problems that they never had. And my research shows that that is new onset mitochondrial dysfunction. So we're taking a problem that started in the mitochondria, and instead of fixing the mitochondria, we put a drug into the system that covers it up, but then it causes its own energetic problems. And if you try to go off of it, you have a whole new batch of mitochondrial problems that you didn't have before. A real mess. If depression starts in the mitochondria, we should be using a mitochondrial approach to treating it. When we think about acne, we should be thinking about vitamin A, zinc, B5, and mitochondrial function before we think about drugs. That's before we think about retinoids. That's before we think about tetracycline. And here I'll show you why. Vitamin A has to be converted to retinoic acid. That's activated vitamin A. And that requires zinc, and it requires mitochondrial function. And what the retinoic acid does is it suppresses the overproduction of keratin, a protein in the skin that is associated with acne inside the acne lesions or the pimples. It also suppresses inflammatory signaling directly in C. acnes, which is a bacterium that is associated with acne. When mitochondria convert food to ATP, as a byproduct of this, they convert NADH to NAD+, or NAD. And you need NAD to activate vitamin A. If your mitochondria are not good at converting food to energy in the form of ATP, as a byproduct of that, they will not oxidize NADH to NAD. But whenever you activate vitamin A to retinoic acid, you use up the NAD and make NADH, and so you need to constantly oxidize that using mitochondrial function in order to keep vitamin A activated. So what is someone doing when they're applying something like Accutane, isotretinoin, to their face? They're supplying a synthetic version of retinoic acid because they don't have the mitochondrial function to activate their own vitamin A, or because they don't eat enough vitamin A, or because they're deficient in zinc. And in fact, there's considerable hypothesis that zinc deficiency is a major factor in acne. On the other side of this, another problem you have in acne is that fatty acids build up in the skin, and you get too much sebum, which contains fatty acids. That sebum then fuels the growth of C. acnes, which feeds primarily on fatty acids. Well, how would you get rid of too many fatty acids in your skin? You would use your mitochondria to convert the fatty acids to ATP and carbon dioxide You breathe the carbon dioxide out, or in the skin it just evaporates, and you don't have an overabundance of fatty acids that are feeding C. acnes growth. You also need ATP to convert vitamin B5 to coenzyme A, or CoA, which is needed for that fatty acid oxidation. So if you don't have mitochondrial function, you're not going to have enough fatty acid oxidation in the skin. The fatty acids build up and they feed the growth of the bacteria that drives acne. And what does medicine do with this? Your dermatologist, instead of fixing your mitochondrial function, gives you tetracycline to kill the C. acnes. But the only reason the C. acnes was there to a degree that's promoting acne is because your mitochondria were not oxidizing the fatty acids. Now, if you take a problem that should have been solved with adequate nutrition and optimal mitochondrial function, and you throw in these synthetic drugs, you wind up with problems. So, for example, Accutane is, although it is a form of retinoic acid, it's 13-cis-retinoic acid. Most of the retinoic acid that you produce in your body is all trans-retinoic acid. Only a small amount are forms like 9-cis and 13-cis-retinoic acid. So now you take this synthetic retinoid and you overwhelm the supply of retinoic acid to primarily be 13-cis-retinoic acid. And that's fine because it helps in certain ways by performing some of the actions of activated vitamin A, but it ultimately hurts you because now it interferes with other important actions of vitamin A. We've seen Accutane tied to depression, birth defects, vision impairment, and sexual dysfunction. And in some of those cases, like the vision impairment and the depression, vitamin A actually helps. So this shows that it's actually interfering with natural vitamin A function. And then tetracycline is actually a mitochondrial toxin. In fact, one of the side effects of high-dose tetracycline is that it causes fatty liver disease. And this is actually quite ironic because to the degree that it is poisoning the respiratory chain and backing up the oxidation of fatty acids and therefore causing fatty liver in the context of high-dose intravenous tetracycline, for example, you put that on your skin and you're killing the C. acnes, but now you're also hurting the mitochondria in your skin, preventing the oxidation of their fatty acids, and you might not have a high enough dose to cause fatty liver disease, but you might inhibit the oxidation of fatty acids in the skin enough to keep feeding the C. acnes and make you dependent on the tetracycline. So acne starts with good nutrition and mitochondrial function as the cures we should be looking to. And if we skip over those, we actually wind up poisoning the mitochondria even further. Now let's take another example of your high cholesterol. What's the doctor going to do? Probably not optimize your mitochondrial function, probably put you on a statin. How do statins work? They increase something called the LDL receptor. And once you understand the biology of the LDL receptor, which is how you clear cholesterol out of your blood into your liver, once you understand the cellular biology of this, it will become incredibly clear why, if you're thinking about trying to control your cholesterol, you have to be thinking about your mitochondrial function. The figure on the top is from Molecular Biology of the Cell by Alberts et al., the Bible of cellular and molecular biology. And what it's showing you is that LDL receptors are present on the plasma membrane, which is the outermost membrane of the cell. And they're connected to this green protein called clathrin, which helps internalize LDL with its receptor. When the LDL binds to its receptor, the membrane invaginates and pinches off, and now you have a coated vesicle that comes into the cell. It has to get uncoated, and it moves to the endosome. The endosome is a compartment that accepts things that enter into the cell this way. And the endosome turns it over to the lysosome, which is the digestive particle or the digestive compartment of the cell. It's like the cell's stomach. And the lysosome digests that vesicle, digests everything inside it, and releases free cholesterol into the cell. So this is LDL in your blood. Now it's free cholesterol in your liver. What statins are doing is they are decreasing the liver's free cholesterol, making the liver say, hey, I need more, making more LDL receptor to move more into the blood. What this diagram is not showing is some detail about the motor proteins involved, which is shown in the figure below. You have to think about this. If the LDL particle comes into the cell because it binds to the LDL receptor, how does it actually move into the cell? It's got to go somewhere. And whenever you see movement, think about what I told you back at the beginning. Mitochondrial energy production is what fuels all movement in the body, and therefore what fuels the putting things in their proper place. So that LDL particle belongs in the liver instead of in the blood. That's energy produced by the mitochondria that has to move it from the blood into the cell. And we can see this demonstrated molecularly in the figure on the bottom. So the cargo in here is the LDL particles. This is the membrane invaginating to be pinched off. But what do we see here is this brown protein called dynamin. This is a protein that squeezes the membrane to pinch it off. How do you squeeze something without energy? Just imagine if you just completed the most grueling workout possible. All your energy is gone. You can't do anything but lie on the couch. Get a dynamometer and test your grip strength. What's it going to be? Nothing. Because if you don't have energy, you can't squeeze anything. So same thing going on here. This protein is fueled by GTP, which is a close cousin of ATP. It is essentially directly fueled by mitochondrial ATP production. If you don't have ATP, you can't squeeze this off the membrane. Now, in order to provide structure to this invagination, we have a protein called actin, shown as the red fibers. And that actin is going to come around the invagination, provide structure to it, and the membrane has to interact with those fibers. It does so with a protein called myosin 6. And that myosin 6, where else have you heard the word myosin before? Well, if you've taken anything that covered the biology of skeletal muscle contraction, you know that as you contract your muscle, you are using the protein myosin. In the muscle, it's myosin 2. Myosin 6 is just another family of myosin proteins. And what do you need in order to contract your muscle? You need mitochondrial ATP production. What does myosin 6 need in order to interact with these actin fibers? It needs mitochondrial ATP. It hydrolyzes ATP to fuel its movement in the same exact way. Now, inside the cell, you may have gotten the impression in your high school biology class that cells are just a sack of water and things are floating around in it. And if you apply that to how do you clear LDL from your blood, you might have thought, well, the LDL receptor just falls into the cell and then just swims around. Cells aren't organized like that at all. And if you studied biology at the college level, certainly if you studied molecular and cellular biology, you know this for sure. Cells are highly organized microcosms of society, and they have essentially a transport superhighway or a very sophisticated railroad system, or however you want to think about it, that's made of this blue protein called microtubules. Things don't float around. They bind to the microtubules and they go on certain tracks to get where they're supposed to be. So if we're looking at the top figure and we're saying, how does the coated vesicle that carries the LDL receptor, how does it get into the endosome? It moves on the microtubules. And what you see in the microtubules here is you have proteins called dynein and kinesins. And these are motor proteins that help this vesicle walk along the microtubule essentially to get where it needs to go. And how do they do that? They use mitochondrial ATP production to power the transport. Not shown in either figure, the uncoating of this vesicle has to happen, and that is going to happen through heat shock protein 70, or HSP. Every single heat shock protein, you may encounter these in explanations of how sauna works, for example. All heat shock proteins are ATPases, meaning they hydrolyze ATP to perform a function involving energy that they harvest from that ATP. So we now have 5 classes of proteins that are ATP dependent, that are involved in moving the LDL from the plasma into the liver cell. And so you can take a drug that's going to target producing more LDL receptors, but that's not going to make the LDL work. If you aren't making mitochondrial ATP, you are not going to be able to control your cholesterol. And if you force your body to move cholesterol from your blood into your liver with drugs like statins, all you're doing, if you haven't optimized your mitochondrial energy production, is you're taking ATP for that process away from other processes that need it. And one reason that we're going to see why that's not wise is that statins are actually mitochondrial toxins. Now, when you're not taking a drug for your cholesterol, how is it usually controlled? Generally, there are two reasons that you make LDL receptors. One is because you have a scarcity of cholesterol inside the cell. It says, I need more cholesterol. And so it'll make more LDL receptors to bring it inside. And the other is you have a state of abundance in the body. When you have a state of abundance in the body, your brain cooperates with your endocrine system to ramp up your metabolic rate, and you want to do productive things with cholesterol, and so you move it into cells that can use it. You move it into the liver, you're going to make bile acids to support your digestion. If you were moving into other cells, you might be making reproductive hormones, you might be making important cellular structures, you might be synthesizing synapses in your brain, and so on. But how is that state of abundance communicated inside the body? At a very high level, think about it this way. Certainly you need to eat enough food for your body to perceive a state of abundance. But if you have an interruption in your mitochondria's ability to convert that food to usable energy in the form of ATP, do you really have abundance? No, you just have calories that you ate and they can't move. They can't be mobilized to do anything. You might get fat, but you're not going to feel energized, and you're not going to have a state of abundance that ramps up your metabolic rate, invests cholesterol into sex hormones and digestion. You are going to have a state of stagnancy. And so the way that this works on a physiological level is that you consume carbs and calories, and in the pancreas, you make insulin. But you don't make insulin in direct response to carbs or calories. Carbs especially, and calories to a lesser extent, influence the amount of insulin that you make, but the mechanism that they influence it by is mitochondria convert them to ATP. And it is the ATP that is driving the insulin secretion. In your adipose tissue, the same thing is true of the leptin that you make. The insulin and leptin then act on the hypothalamus to produce thyroid releasing hormone, or TRH, which goes to the thyroid gland to make thyroid hormone. But how does that happen in the hypothalamus? It's not a direct signaling. It is actually insulin and leptin act on the hypothalamus to increase mitochondrial ATP production, and the ATP drives the TRH. And the TRH then goes to the thyroid gland, and alongside insulin acts to increase thyroid hormone. And then the thyroid hormone increases the LDL receptor production. Now, in this case, we have genuine communication of a state of abundance that truly exists in the body, and that state of abundance is correlated to the useful utilization of cholesterol. If we start throwing things into the mix, like exogenous thyroid hormone, we will ramp up the metabolic rate, we will do useful things, but we could run into a wall where we are falsely communicating a state of abundance. If we're taking statins, we're not creating a state of abundance at all. We're not even creating abundant signaling. We're creating scarcity signaling by inducing a cholesterol deficiency in the liver. That's, on the one hand, they're bringing cholesterol down in the blood in the same way by making more LDL receptor, but they're making more LDL receptor for two totally different reasons. And if you have the choice between operating in a state of abundance versus a state of scarcity, you always want to choose abundance. In his 1976 book, Solved the Riddle of Heart Attacks, Broda Barnes reviewed the history of how thyroid hormone was used to control heart disease prior to the release of cholesterol-lowering drugs. And in fact, thyroid hormone could linearly lower cholesterol in the blood, regardless of whether the dose was excessive or not, regardless of whether the person initially had hypothyroidism, because that's what thyroid hormone does to the LDL receptor. It makes more of it. And if you have even if you have more thyroid hormone than you need, all that's communicating is that you have an even greater state of abundance. The problem with that was that because the effect on cholesterol was not directly tied to the degree to which someone was hypothyroid, then practitioners got overzealous with their treatment of the cholesterol, and they actually killed a few people through irresponsible dosing, and that's why it fell out of favor. And you can look at that and you can say, it might be best to start with actually using nutrition and lifestyle to create the state of abundance instead of trying to throw an exogenous hormone in to communicate a state of abundance that's not there. Nevertheless, as Barnes was pointing out, you could be much more conservative and responsible with the thyroid dosing, and it would be effective. And in fact, it was effective for decades prior to the 1970s. So as I was just saying, statins are primarily acting on blood cholesterol by decreasing the cholesterol synthesis in the liver. That induces a deficiency of cholesterol in the liver. The liver makes more LDL receptor to deal with that scarcity. The problem is that statins don't act directly on cholesterol synthesis. They actually act on the synthesis of a compound called mevalonate. Specifically, statins come in and they block mevalonate production. The problem with that is that although mevalonate is used to synthesize cholesterol, it's also used to synthesize coenzyme Q10 or CoQ10. It's also used to synthesize heme A. And heme A might sound to you like hemoglobin because that heme is related to the heme that is part of the hemoglobin molecule, how you transport oxygen in your blood in order to provide mitochondria with it. Heme A is actually an iron-based protein that you use in the respiratory chain at the point of oxygen utilization. And so if you interrupt the synthesis of heme A, you are creating an acquired deficiency of mitochondrial function at the point of oxygen utilization. Coenzyme Q10 is also used to produce ATP in the mitochondria. So you've got a double hit against ATP production. As we talked about when we were covering depression, ATP is needed for methylation. But methylation is not only needed for the production of all mitochondrial proteins and therefore for ATP production itself, it's also needed to produce creatine. And when you add statins to cells, they decrease creatine synthesis. And there is some urinary measurements in human studies that suggest that at the doses they're used to treat high cholesterol, they are decreasing creatine synthesis. And creatine is the mitochondrial power grid. It is used to translate the power of mitochondrial ATP throughout the rest of the cell and therefore used to use ATP. And that means that ATP itself and creatine also are needed to use ATP to support the motor proteins that bring LDL cholesterol into the cell. Creatine is also used to support methylation because ATP utilization is also needed for that. And so if you lack creatine, you are also creating a vicious cycle. And you now have the opportunity for two vicious cycles to operate in tandem. You have low ATP means low methylation, means low production of mitochondrial proteins, means compromised ATP production. And you have low methylation means less creatine. Less creatine means less methylation. This vicious cycle then feeds this one, and the two vicious cycles become a vicious super cycle together. So people say, statins, oh, you just got to take CoQ10 with it. Well, there's a couple of problems with that. One is that you cannot fix this problem just with CoQ10 because there's no supplement that you can take to fix the deficit of heme A production. There is no supplement in existence that will fix a deficit in heme A production. So CoQ10 will help, but it's not going to cut it. Now you can take creatine, and yes, that can help interrupt the vicious cycle, but it's not going to help the heme A production. And so there are elements to this that their only solution to this is to not be on the statin. And there are things that you can do to help, but nothing that you can do to help completely. Why is this a problem? And do we know it's a problem? Well, some people will shoot back and they'll say, well, Chris, there are so many randomized controlled trials of statins. We know exactly what they do, and we know that they're a safe and effective way to reduce heart disease deaths. Well, we also know that they produce a predictable rate of statin-associated myopathy. The myopathy is due to mitochondrial dysfunction. There's also evidence that statins promote diabetes. Why do they do that? Because mitochondrial function causes diabetes. But let's just take the myopathy as an example, because this is the more well-established and accepted side effect of statins. There's a lot of controversy over the rate. And part of the problem is that just as with SSRIs, where the trials showed them to be way safer for withdrawal than the observational studies do, and in that case, the discrepancy is primarily a result of the fact that the trials are 8 to 12 weeks long, and in the real world, they're used for 5 years or longer. In this case, the discrepancy is probably more driven by mostly by the health of the people that go on them, and probably to some extent is in cases that take a while to onset might be due also to the fact that in the real world, people, again, use them for way longer than the trials are done for, because the idea behind statin use is the earlier you put the person on the statin, the lower their cholesterol. They have lower lifetime exposure to high cholesterol levels, and so you can put them on for decades, and the randomized controlled trials aren't generally going decades out. When you look at randomized controlled trials, people are they're not random samples of the population. The people that choose to participate in randomized controlled trials are healthier than other people to begin with. And then also the trials don't want to show high rates of myopathy. So the trials can filter out predispositions to myopathy in a way that a doctor screening their patients is not going to usually. And then on top of that, what do you count as myopathy? So do you count the person who has an unexplained increase in cramping as having myopathy, or do you only count them as a case of myopathy if they go to ER with rhabdomyolysis, which is a serious and sometimes fatal condition where the muscle breakdown is causing red and brown colors from muscle proteins to leak into the urine? Depending on how tightly you define myopathy, you might see different rates. But the clinical trials say 1.5 to 3% of people are going to get statin-associated myopathy, and the observational studies say anywhere from 7 to 38%. So it's probably a bigger problem than the trials are admitting due to the factors that I just discussed. There are a number of trials looking at whether CoQ10 can help. There have been meta-analyses of those trials that have said they don't help. CoQ10 doesn't help at all. And there are meta-analyses that say that it's very effective, but it reduces the rate of muscle pain by about half. The main difference between those meta-analyses is their inclusion criteria. The meta-analyses saying that CoQ10 does nothing have more rigorous trial inclusion. For example, they require creatine kinase, which is a biomarker of muscle damage, to demonstrate the myopathy, and they filter out anything that wasn't placebo-controlled. Whereas the trials saying that CoQ10 can cut the muscle pain down in half, the meta-analyses that conclude that are using trials that are not all placebo-controlled and using trials that may have only confirmed myopathy with surveys about muscle pain symptoms. The point is, CoQ10 can do anywhere between nothing and cutting the muscle pain down in half, but it's not going to completely resolve the muscle pain. There are studies of creatine supplementation where creatine has completely resolved statin-associated myopathy, but that's only demonstrated in one case series of 13 people and one individual case report. So across the board, we don't have a firm solution to this. We have CoQ10 and creatine as things that would help, but you have a level of mitochondrial dysfunction going on that has at least a component with no solution to it. And you also have the opportunity for this vicious supercycle to create all kinds of secondary energetic effects. There was a metabolomics study of statin-associated myopathy, and it showed all kinds of disruptions to energy metabolism. Some of the major ones were glycine and serine metabolism being disrupted, probably as a result of interfering with methylation, a massive shift away from branched-chain amino acid metabolism and toward arginine and proline metabolism. This is amino acid catabolism being shifted probably as a result of deficits in coenzyme A. And we also see that there are idiosyncratic metabolomics. For example, some people have increased carnitine synthesis, some people have decreased carnitine synthesis. So when you're looking at something like this, you really want to do actual mitochondrial testing to see what are all the secondary effects that have gone wrong, as well as what were the mitochondrial vulnerabilities leading into that made that person predisposed to the myopathy. But the real problem is that no one was ever thinking about mitochondrial function to begin with. What you're doing here is you are using statins to pump up the LDL receptor, but you're using a drug that is a mitochondrial poison that decreases the ATP needed to fuel the movement of the LDL receptor from the blood into the cell. Now you are taking a limited ATP supply, you're diverting it to the LDL receptor, so you do get the drop in cholesterol, but you're taking it away from everything else that needs it. What needs it? Everything else in the cell. Your longevity needs it. So this is kind of like if you were managing a country and you have an oil shortage and you say, oh, if I have an oil shortage, I'm going to have less gasoline, I'm going to have less people getting from A to B. Less people getting from home to work, from work to home. What am I going to do to transport more people? I'm going to import more cars. And so you import more cars, but you also deny drilling permits in your country. And so you cut the oil supply in half. You divert the fuel that you do have to importing the cars. Now you have the cars, they're getting more people from point A to B, but they are taking that oil away from other uses. So you've got people that are using it to heat their homes, and now they're going cold in the winter. They're developing cardiovascular and respiratory problems, hypothermia from it. The children are frostbite. The grandparents are dying. So when you are focusing on using a mitochondrial toxin to lower cholesterol, you are looking at that one marker and you're succeeding. But what is happening as a cost to that, that's what is being overlooked. So I went through 3 examples of why you should always be thinking about mitochondria first. If you think about mitochondria first in the case of depression, you are going to optimize methylation and brain energy capacity to deal with stressful thoughts and situations, and you're not going to trap yourself into a damned if you do, damned if you don't mitochondrial vicious cycle of getting on drugs that ultimately make the initial problem in your mitochondria worse and then make it even worse when you try to go off the drug. If you think about mitochondrial function and nutrition first, in the case of acne, you're saving yourself the side effects of using an imposter form of activated vitamin A that is ultimately interfering with a lot of important functions of natural vitamin A, and using antibiotics to try to target bacteria that are only being fed because of the initial mitochondrial dysfunction, just to make mitochondrial dysfunction even worse. And in the case of statins, there might be legitimate uses of statins, but you should be dealing with mitochondrial function first. You should be dealing with food first, and you should optimize your ATP production so that if you do need to do something like a statin or red yeast rice, you are doing it from a state of mitochondrial ATP abundance, and then you can divert that ATP to the specific goal you're trying to do, but you have an abundance of ATP to fuel everything else that you need in your body, instead of going first to the mitochondrial poison that's going to make the mitochondrial problem worse and then only be able to achieve the goal of lowering cholesterol at the expense of many other goals. So I hope I've made the case to you that you should think about the mitochondria first, but I also now want to cover why targeting mitochondria without testing can actually be dangerous. I'm going to give you 3 examples. One story of someone I know, I'll call her Jane. She had trouble swallowing, and she often felt worse upon standing. So she had orthostatic problems. And she was diagnosed by a practitioner with dysautonomia, which is disruption of autonomic function that controls things like changes to hormones, blood pressure, heart rate, etc. when you go from sitting to standing, for example. That practitioner had their own experience where a ketogenic diet and high-dose thiamine had resolved their dysautonomia. So the practitioner put Jane on the same regimen, high-dose thiamine and a ketogenic diet. But Jane got 5 times worse on that regimen. In fact, she got so bad that she could not eat unless she was lying down, because just going from lying to sitting took so much energy out of her that she didn't have any left over to swallow, to the point where it started to look like it might not have been really an autonomic function issue. It might have been more of a straightforward lapse in energy production. Well, it turned out that the reason that she got worse, which could only be revealed through mitochondrial testing, was that she had a specific problem oxidizing fatty acids. And when you look at the pathways where you have fats going in one way and you have carbohydrates going in another, she had that specific block in the fatty acid oxidation. That indicated that the thiamine probably wasn't the problem. It was really the ketogenic diet that was the problem for her. But mitochondrial testing was able to reveal actionable reasons why she couldn't tolerate the fats, such as she needed CoQ10 to be able to tolerate them and so on. And that allowed her to shift the diet towards carbohydrates and away from fat, incorporate the proper supplements, and then start being able to eat normally, stand up, and even start exercising. Example 2 is someone I know, we'll call her Emily. She was suffering from fatigue, and she rated her energy at 0 and felt like she couldn't even get off the couch. And a practitioner put her on 1,100 milligrams of thiamine. In this case, the thiamine, she didn't go on a ketogenic diet. The thiamine led to new onset motor dysfunction, difficulty coordinating her movements, unsteady gait, and aggravated existing problems a lot, making dizziness a lot worse and episodes of blurry vision a lot worse. In this case, the thiamine in particular seemed to be a problem. And mitochondrial testing after all that happened showed that she had a broad deficit in the mitochondrial respiratory chain, which is the central set of engines involved in ATP production. And it's the final step in the oxidation of food to produce ATP. The problem with thiamine is that thiamine activates early steps in the breakdown of food products to produce ATP. So if you got a limitation in the respiratory chain, the thiamine is just basically dumping energy on the bottlenecked problem, and now you have a traffic jam of energetic flow, and that traffic jam then leads to reactive oxygen species production and other damaging things that actually hurt energy production. So months of thiamine withdrawal, gently raising all the nutrients that were important for the deficient parts of her mitochondria, and combining that with physical therapy allowed her to achieve healthy movements again. But this is a great example where something that helps a lot of people can hurt someone if you're not actually looking for what their underlying problem is. Third example, someone I know we'll call George. He was suffering from chronic fatigue, and he tried 1 milligram of methylene blue twice a day. Now, there are people that rave about methylene blue, how it supports their energy, their healing. It's great for mitochondrial function. Well, he responded with worse mood. He was more irritable, more indecisive. He had mild anxiety, impaired short-term memory, slightly less sleep, but increased need for sleep, leaving him more overall fatigued during the day. After that experiment, mitochondrial testing revealed that he was not a candidate for methylene blue, could have avoided that in the first place, and showed that his best operating energetic pathway was to use the amino acid cysteine for fuel. And that both explained why he had done best on a steak-centered carnivore diet, which is high in cysteine, and it also carbohydrate restriction also promotes oxidation of the cysteine for energy. But it also allowed him to substantially improve his fatigue by using strategic supplementation with cysteine instead of only relying on steak. So these are examples where you can think about mitochondria first, but sometimes what you're thinking about is doing more harm than good because you thought about the mitochondria, but you didn't think about what specifically was wrong with the mitochondria. Now I want to show you two examples from the literature of how there are downsides to generic mitochondrial supplements that are demonstrable in clinical studies. What we're seeing on the screen are the effects of meta-analyses of clinical trials with CoQ10 against systolic and diastolic blood pressure on the top and against glucose and insulin on the left. And we can make a few points. So first of all, I should say that there are many clinical trials demonstrating many benefits of CoQ10. And I'm not comprehensively representing them on this slide at all. But my point is simply that we can see that too much CoQ10 can get you in trouble when you're not using a data-driven approach to your supplementation. So for example, when we're looking at blood pressure, you can see that there are optimal dosing around 100 to 200 milligrams per day. But as you go up in dose, you start to lose the effect, and then you start to actually make things worse than baseline by the time you're getting up to 400 milligrams a day. But you also have a lot of variation around these higher doses. So there are spots where there are, people doing considerably better and people actually starting to do worse in those areas. And you see the worst result overall where for diastolic blood pressure, there's still an average optimal effect between 100 and 200 milligrams, but you actually have a sliver of people just based on the imputed variation. You have a sliver of people whose blood pressure is getting worse there. And so that indicates that the majority of people would do well at a dose of 100 to 200 milligrams of CoQ10, but some people are going to get slightly worse as a result of it. If you look at glucose and insulin, you have a relatively similar pattern. One of the problems here is that where you're seeing the peak benefit, in the case of glucose, it's around 200 to 300 milligrams. In the case of insulin, it's closer to around 200 milligrams. You actually have the widest variation around these points, which you don't observe in all studies. A lot of times the optimal point has the narrowest amount of variation because you're actually hitting a global sweet spot across people. You don't see this in this data. The blood pressure data and the glucose and insulin data have really wide variation confidence intervals around what appears to be the optimal dose. And when you're looking at the average data, it still looks like, yeah, it's the most variation, but you should just shoot for the peak effect. But when you have these big amounts of variation, you're probably getting people who are maximizing their own personal benefit at quite different spots around this line, hence that really great variation. And then you also have this similar effect as you have with the diastolic blood pressure, where the average person is getting worse at the highest dose, but you still have people that are benefiting there. And you get this overall picture that if you had to place your bets on a dose, you would probably place it at 200 milligrams of CoQ10 to try to hit the best of all worlds. But at the end of the day, it also looks like there's just going to be a lot of variation between one person's needs and another's. We also don't really know what the lifelong outcome of high-dose CoQ10 is. It may well help a lot of people, but one study in mice suggests that CoQ10 across the lifespan worsens spatial learning, memory, and age-related hearing loss. And high-dose CoQ10 in the context of Parkinson's patients has caused, from case series, things like orthostatic hypotension, acid reflux, heart palpitations, and hypocalcemia. So CoQ10 doesn't seem as for everyone. And from anecdotal experience, a lot of people who try normal doses of CoQ10 wind up with things like insomnia, heart palpitations, anxiety, a general feeling of overstimulation or oversensitization to sounds and stimuli. And the net result is you're much better off if you have testing that can show whether you need CoQ10 or not. People say on the internet that methylene blue is going to optimize your mitochondrial ATP production, but here's why it could actually make you worse. Animal experiments show that methylene blue acts by rewiring your mitochondrial respiratory chain, the engines where you make energy in the form of ATP from the food that you eat using the oxygen that you breathe. And the fact is, there is no better path for energy utilization than the one you were naturally born with, assuming that you're well nourished and everything is working properly. If you have a bottleneck there, methylene blue can help go around it. But if you don't have a specific bottleneck, methylene blue can just randomly rewire the flow of energy, and it's going to take it away from the optimal, efficient pathway that you were born with. And that's why you can see in the bottom figure here, what you see is the result of animal experiments where below 0 to -5 represents a drop in ATP, above 0 up to +5 represents an increase in ATP production. And what you can see is on the left is what happens to ATP if you don't have anything blocked. On the right is what happens if you do have a block in your respiratory chain. And the simple result is that you get a decrease in ATP if you don't have a block. You get an increase in ATP if you do. So people who are benefiting from methylene blue are benefiting because they have a problem. But I told you before about one person who I named George who tried methylene blue and wound up getting a very negative result because of it. To make matters worse, George was not alone. In fact, in clinical trials of Alzheimer's disease, we saw no benefit to cognition. We saw an dose-dependent increase in the dropout rate, and we saw an 8-fold increase in the risk of injuries from falling. Now, there are definitely highly valuable uses for methylene blue in medicine. There is evidence that its monoamine oxidase inhibition activity can help with depression. There are antimicrobial benefits. There are benefits when it's used in surgery, when it's used in imaging, when it's used for poisonings. But it also has negative consequences like increasing reactive oxygen species. And ultimately, it rewires your energy production, which you want if you have a problem. If you don't have a specific problem that makes you a candidate for methylene blue, it is going to wind up hurting. All right, so I've made the case for you that you always want to think about mitochondria first, that when you do think about mitochondria, you don't want to be generic about it. You want to use data. And I've given you examples from the literature how in general we're seeing that just generally throwing mitochondrial cocktails at things does have its downsides. I now want to show you the true power of testing. Now, I want to talk to you about my product, Mitome. Mitome is an at-home cheek swab analysis of mitochondrial function that builds you a personalized protocol to transform your cellular energy. I developed Mitome. I am the founder and scientific director of Mitome, and I invented the interpretive algorithm that is laid onto a type of mitochondrial testing that was up to this point reserved for rare disease specialists. And I took it out of that and cross-referenced it with thousands of clinical studies that I've analyzed, as well as hundreds of cases where I have been able to cross-reference mitochondrial testing with whole genome sequencing and comprehensive metabolomics, meaning amino acids, organic acids, nutrient concentrations, metabolic panels, acylglycines, acylcarnitines, correlating the mitochondrial testing with the entire battery of biochemical knowledge. And I spent a couple of years where I developed personalized protocols for people that would often take me up to 2 months with thousands of dollars of testing to do. And I wanted to ask the question, what out of what I'm doing can I leverage to make this far more accessible to the common person and at the same time get really high ROI results for much less time and much less cost? And the answer is mitochondrial testing is at the heart of it.
As we go through these stories, it is important to note that Mitome is not intended for the diagnosis or treatment of disease, but is rather meant to help you optimize your mitochondrial function to support maximum wellness, performance, and longevity. Although we are about to discuss stories involving medical conditions, this content is not meant as medical advice and is for educational purposes only.
One customer, Jacqueline, went into unexplained menopause or amenorrhea at the age of 28, which is, obviously not old enough to expect menopause. And that lasted for 10 years. Conventional medicine, functional medicine, homeopathy, alternative therapies, diet, fitness, everything she tried, nothing worked. Mitochondrial testing showed that she had a highly specific and unique need for CoQ10. Within 2 weeks of supplementing, she got her period back. Absolutely stunning. Case number 2. Miguel was a customer who had no health issues at all until after being on Paxil long term. He went off Paxil for the first time and then went back on Paxil and developed tachycardia and muscle cramps, then switched to Lexapro. And switching to Lexapro made everything worse, and then went off Lexapro and then had a whole new battery of problems. And these included sexual dysfunction, peripheral neuropathy, shortness of breath, anxiety, muscle cramping, numbness, and excessive urination. So mitochondrial testing showed that he had a highly specific problem transporting methyl groups in the form of S-adenosine methionine or SAMe into his mitochondria that led to a pattern in his mitochondria that could only be caused by a global deficit of methylation inside the mitochondria. He had gone to dozens of specialists who couldn't help him at all, but the protocol that he got to support mitochondrial methylation, 6 weeks into it, he reported that it was the first time he had felt normal in over 2 years. He wrote back at the 6-month mark and said that 6 months later, quote, "I have regained quality of life and am able to do everything I used to be able to do." And then at the 8.5-month mark, he said that he was completely amazed at the benefits that he got from the protocol. He felt like a whole different person from a year ago. He said it was totally wild. He gained close to 15 pounds of lean muscle mass 2/3 of the way through the year since January. And he was making gains in the gym daily. And he told me a few months ago, he told me that he was expecting to add another 10 pounds by the end of the year. Now, this sounds crazy. It doesn't make any sense. So I reached out to him recently and I said, "How is the muscle coming along? Also, do you have any measurements? Because this sounds kind of wild." Because he's talking about gaining 25 pounds of muscle in a year. So it looks like he's going to end the year at a 17-pound gain in... To me, it looks like, I'm sure he gained a couple of pounds of fat, but it's mostly muscle to keep his body fat. His observation is he's putting on 17 pounds. He doesn't look any fatter. His testing doesn't reveal he's any fatter. So, his body fat percentage is staying the same. It's mostly lean muscle that he's gaining. To make sense of that, the reason he's able to gain so much is because he's regaining what he had lost during his sickness. Nevertheless, he went through years where not doing any testing was just not getting him anywhere. And it was testing with Mitome that ultimately led him to regain his health. I'll give you one more example. Anita had triple negative breast cancer, went on chemotherapy, and a year after the chemotherapy, she was still struggling with deep fatigue, brain fog, and scars that did not heal completely. Now, if you look in the literature, a single round of chemotherapy for breast cancer actually causes dramatic mitochondrial dysfunction that can be seen on a skeletal muscle biopsy. In any case, her Mitome protocol emphasized highly specific amino acids and organic acids that would funnel into mitochondrial energy production to bypass routes that were blocked. that showed the least resistance to energy flow. And she reported that the surge in cellular energy that she experienced allowed her to start a strength training program, replace muscle lost to atrophy from the chemotherapy, and there was scarring that had gone nowhere for an entire year. It was completely static, and it completely healed when she was on her protocol. And her autoimmune issues that had been flaring up finally cooled off. I remember when she had sent an email about 2 weeks into the, actually it was 1 week, her first week on the first organic and amino acid supplements in her protocol. I remember her saying that she hasn't been able to work really a full day the entire time, and she got 4 full days of work Monday through Thursday. So these were, results that came in really fast, but a year out, and she was able to report incredible gains, and that all came through testing with Mitome. So let's talk a little bit about what we're actually testing, what we're looking at by looking at mitochondrial biology. This is a diagram of the cell, and you can see that the cell has an outer membrane called the plasma membrane, and then it's got all these little organelles inside, which are specific components that fill specific purposes. It's kind of like you having different organs that do different things. On the cellular level, you have organelles that do different things. And the mitochondria is this squiggly guy right here, responsible for energy production. Now, in between the organelles, you have what's called the cytosol. The cytosol is the general fluid between the organelles. It's the general area of the cell. When you're in the cytosol, you're not inside any particular organelle. And if you think of this as a house with many rooms, the cytosol would be the hallway. It's what connects everything together. You have effectively 3 main sources of ATP production in your cell, and there is one of them called glycolysis that acts in the cytosol. If we think of the mitochondria as the powerhouse of the cell, and the mitochondrial respiratory chain or electron transport chain as the power plant, glycolysis in the cytosol is essentially a local power generator. It can be very useful at times for a local production of energy, but overall it's not a major source of the bulk energy in the cell. And in fact, under different conditions of carbohydrate versus fat burning, we can break it down a little bit differently, but ultimately 90% of your energy is formed in the electron transport chain, or the respiratory chain, it's also called. And you have a small percentage produced in the citric acid cycle, also known as the TCA cycle, and a small amount from glycolysis. The general pathway by which you're going to metabolize any fuel for energy is you're going to start with a macronutrient like fat, carb, or protein. You are going to feed those into the citric acid cycle, or the TCA cycle. That happens in the mitochondria, and then that is going to feed the energy into the electron transport chain, or the respiratory chain, which also happens inside the mitochondria. Your mitochondrial function is pointless if you are not taking creatine, or at least if you're not optimizing your creatine status. And the reason is that creatine is like the mitochondrial power grid. So if mitochondria are the powerhouse of the cell, the respiratory chain is the power plant, creatine, through the creatine kinase reaction, is the grid that carries that energy throughout the rest of the cell, especially into the cytosol. Most people who are not eating 1 to 2 pounds of meat or fish per day are going to need to supplement with creatine to some degree in order to optimize their creatine status. Since 90% of cellular energy in the form of ATP is made in the mitochondrial respiratory chain, the respiratory chain is where it's at in terms of optimizing your cellular energy. And this is made of several distinct components. There are 4 major complexes that are involved in oxidizing food energy. These are complexes 1, 2, 3, and 4. And CoQ10 is a nutritionally important molecule that carries electrons from complex 1 and complex 2 to complex 3. Because each of these complexes has unique nutritional needs and abilities, and because everyone has genetic variation as well as nutritional and lifestyle variation that impact the respiratory chain, we can learn a tremendous amount about your unique needs by measuring the activity of each individual complex. So Mitome, instead of simply telling you your mitochondria are good or your mitochondria are bad, or telling you something like your mitochondria are not making enough ATP or they are producing too many reactive oxygen species, Mitome is actually telling you whether your complex 1 is doing well, 2 is doing well, 3 is doing well, 4 is doing well. And it is looking not only at whether they're high or low, it's also looking at the ratios between them and the specific patterns involved that become apparent upon the results in order to infer what is underlying the mitochondrial function and what can be done about it to meet your unique needs. There's variation, for example, that complex 4 is the only complex that requires copper. Complexes 1 and 2 require riboflavin, but 3 and 4 don't. And there are different pathways for fat versus carbohydrate versus protein to feed into the respiratory chain. And so seeing these patterns can allow us to produce a personalized report that tells you which fuels would be best for your mitochondria. And if there are limiting bottlenecks, how can you either fix them or work around them in order to optimize your own unique cellular energy production? So just to give you a few snapshots about what the report looks like, your report will tell you the activity of each complex and rate it against where it should be. The protocol that you get is highly personal, so the supplements are unique to you. We are not reporting the same generic recommendations for everyone that can benefit the mitochondria, but we're looking at what are the most unique things that you need. And as a result, you should not assume that your report is going to apply to anyone else. And we are also ordering the recommendations in a specific order to test one at a time, both to guide you through the process of verifying empirically what works best for you. Your protocol also gives you the correct sequence in which to implement each step. Above, you can see a protocol snapshot that gives, in this particular case, all the different elements that the person will be implementing. And you can see an example of a step with this person has alpha-ketoglutarate in their protocol. You can see it's step 6 in this person's protocol. It's dependent on what they found in step 3, and it gives a lot of detail about how to implement it, what to look out for, how to optimize, and so on. Part of the reason we put so much care and curation into the order of the protocol steps is that energetic bottlenecks are like traffic jams. If you are mega dosing a mitochondrial nutrient, you can run that right into a bottleneck with a higher nutrient demand that just causes the equivalent of a car crash inside your mitochondria. And this is what explains some of the cases that I talked about before where high-dose thiamine worked amazing for one person and caused months of extended problems for other people. Now, the optimal approach would be to actually fix the traffic by expanding the capacity. But sometimes you might have a genetic problem. We're not going to be able to fix the bottleneck. What we can do is we can provide a detour to work around it, to reroute the flow of energy so that you still get your energy where it needs to go. You're just skipping over a step that's not working well for you. So if you look at the flow of energy in this diagram, you can see that the catabolic breakdown of macronutrients, fat, carbs, and protein, and running the citric acid cycle is leading you into the electron transport chain of the respiratory chain at the end. If you follow this direction, the last thing you want to do is fix a problem up here without having fixed it down here. In other words, you don't want to fix your ability to break down carbohydrate and allow it to enter the citric acid cycle if you have a problem in the respiratory chain that you haven't fixed, because now you are going to have the energy that you've released just run into another bottleneck and cause the equivalent of a car crash. Inside the respiratory chain, we have multiple opportunities for detours, things we can fix, and possibilities for traffic jams to exist. As an example, if your complex 3 is not functioning well, we can reroute energy around complex 3 in a detour to complex 4 with certain supplements. On the other hand, it might be that your complex 2 is not working well, and that's because of nutritional deficiencies that we can fix. So wherever possible, we always want to fix what we can fix, make detours around what we can't fix, but we also want to do so in an order that will never cause a traffic jam. For example, if we have a problem in complex 4 and complex 2, we don't want to fix complex 2 first because it's just going to create a traffic jam at complex 4 and risk the equivalent of a car crash. So we're always trying to free up the energy flow, but we want it to actually be able to reach the destination. So we're freeing it up at the point of the destination and then allowing the earlier steps to be fixed. A lot of people ask, how is this different from organic acid testing of mitochondrial function? The reality is we are testing something fundamentally different. I love organic acid tests. I've used them a lot. They are highly valuable. But organic acid tests are looking at mitochondrial function from the perspective of the early phase of energetic traffic. They're looking at the catabolic breakdown of fat, carbs, and protein. They're looking at the function of the citric acid cycle. They're not looking at the respiratory chain. Mitome is looking at the final destination. Again, it's not that these things aren't worth fixing. It's that you never want to fix something in the early phases of energetic flow until you make sure that the energy is able to arrive safely at its destination. Another way to think about it is if the early phase is your house, the respiratory chain is your foundation. You don't want to build a house on a foundation of sand. You want to build your house on a solid foundation. Ultimately, what Mitome is able to tell you is from the perspective of your mitochondrial engines that produce your ATP, do you burn carbs or fat better? What vitamins and minerals do your mitochondria need for optimal function? Does it matter what order you put them in? Should you use CoQ10 at all? And should you use CoQ10 or should you use MitoQ? Are you a candidate for methylene blue? Do you need to adjust your location or your health practices to modify your oxygen exposure? Are certain toxic exposures hurting your mitochondria? And a lot more than that. There are other mitochondrial tests on the market, and I'm not going to name names, but they tell you things like you're not producing ATP, or you're producing a lot of reactive oxygen species, or your mitochondria are doing great, or your mitochondria are doing awful. But they're not looking at the details of the individual components of the mitochondrial energy engines that produce your ATP. And so they're not able to tell you what the highly unique limiting bottlenecks are to you. So Mitome is not about testing your mitochondria. It's about testing what the specific limiting bottlenecks are in your mitochondria so that you can learn how your cellular energy production would respond that would be different from mine. Of course, there are things that we should all be doing for our mitochondria, and I'll give you my top 5 so that you can go home with something that you can go out and apply right now. I mentioned creatine. If the mitochondrial respiratory chain is the power plant, creatine is the power grid. If you're not optimizing your creatine, your mitochondrial function means nothing because the energy can't go out from the mitochondria to nourish the rest of the cell. I'm not saying that everyone needs to supplement creatine, but in general, you can get creatine from your diet if you eat between 1 to 2 pounds of animal flesh per day. So you can err on the side of 1 pound if it's red meat or salmon, and if it is lightly cooked. You want to err on the side of 2 pounds if it's white fish or white meat, and if it's well done. As a vegan, it is possible that you are getting enough methyl support and protein to meet your own creatine needs, but if you're on a 2,000 calorie vegan diet, it would have to look something like you are eating a ½ kilogram each of tofu and quinoa. Might there be some people outside of those boundaries that don't need to supplement with creatine, yes. But most people outside of those two dietary patterns really should be supplementing with creatine. You can supplement with 5 grams a day for a month and your muscle stores will be saturated, or you can supplement with 20 grams a day for 4 to 5 days and your muscle stores will be saturated. After your muscle stores saturate, you then need to recalibrate what you're looking at for a maintenance dose, because the distribution of creatine is going to start changing after that. So reach saturation first, then play around with your dosing. Titrate up slowly from 2 or 3 grams at the bottom, maybe go up by 1 gram per day per week, and titrate up until you get to the point where you empirically observe the maximal benefit. Is it benefiting your sleep? Is it benefiting your fatigue? Is it benefiting your gains in the gym? Make sure you're getting something that you can measure of benefit out of it, and titrate up possibly up to 20 grams a day, probably coming out somewhere between 3 and 8 grams a day. The next is sunlight. Red light, near infrared, and far infrared all have a lot of empirical demonstration of their benefit. But there are other wavelengths of light that are less appreciated. For example, too much blue light is bad for you, but there are blue and green wavelengths that do have benefits to your mitochondria. All of the benefits of red, near infrared, and far infrared light, as far as we know, are due to improvements in mitochondrial ATP production. So because of the breadth of the different wavelengths that are necessary, the most important source to go after is the sun. If you're going to try to chop it down to the most simple recommendations you can get, I would say 30 minutes of unprotected sunshine in the morning. If you wear glasses, I would not wear them if you can get away with it, just to make sure that all the wavelengths are getting in. 30 minutes in the morning, and depending on your skin color, at least 5 or 10 minutes in the afternoon. You want to get the afternoon unprotected sunshine to get adequate vitamin D. If you have light skin, it might be 5 minutes. If you have very, very, very dark skin, it might be up to 2 hours. You can certainly get it more efficiently if you wear less clothing and if you sunbathe laying down and turn over halfway through than if you're standing or walking, simply because of the angle that the sun is hitting. If you cover those two bases, that is the most basic thing you can do. But I do think that the optimal environment would be, as long as you don't have respiratory problems, some exposure to fire, because fire provides far infrared. And I can't say that there's any proof that you need to have the combination of red, near infrared, and far infrared, but there are empirical benefits for all of them. And if you look ancestrally, what would our lifestyles look like? Up until modern tools, humans were always exposed to fire, which rounds out and completes the infrared spectrum of the sun. So I do think that exposure to campfire, or I personally don't have fire exposure, so I use a far infrared sauna for a few minutes a day. Feels like it works. It makes me feel better. So I make it part of my routine. And to me, that's a replacement for exposure to the campfire. It is definitely natural to hide from the sun, for example, in equatorial areas for the few hours when it's hottest during the day. So it definitely is not the case that you should try to always be in direct contact in the sun. But I do think that the more you can fill your day with indirect sun exposure, the better. So if you could practically do it, if you could spend the whole day outside, that would be best. But that doesn't mean you want to be unprotected from the sun and right under the noon sun. It's going to burn you. So you do want to use protection from the sun, ideally not chemicals, and use clothing, umbrellas, broad sun hats, etc. But your eyes should be mostly exposed to natural lighting whenever possible. If you have to work indoors, or you simply prefer it because of the weather, then try to work in rooms where you have exposure through the windows to natural lighting for most of the day, and don't have to turn on the artificial lighting. The time where you'd want to think about red light devices, near infrared devices, and far infrared devices like heat beds and saunas is the point at which you are clearly getting benefits from red and infrared light, but you are going to get burned if you spend too much time in the sun. The devices allow you to get more of the therapeutic wavelengths without the wavelengths that will burn you. But you can also simply extend the amount of time you spend out in the morning or that you spend out near sunset, because during those times you get beneficial wavelengths, but you are not getting wavelengths that are going to burn you. So if you can get outside around 7 or 8 in the morning, you could, in most locations, spend up to 10 a.m. in the morning before you really have to start worried about getting burnt. Number 3 is exercise. In principle, exercise is going to stimulate mitochondrial turnover, both clearing of damaged mitochondria and biogenesis of new healthy mitochondria, and is going to nourish the capacity of those mitochondria. And it's going to do it in a way that specifically benefits whatever you're exercising. For example, you do need more mitochondrial function to support endurance than you do a hypertrophy workout. So in a sense, you're going to stimulate more mitochondrial density for the endurance workout than you would for the hypertrophy workout. But the hypertrophy workout is going to work your mitochondria in a way that supports the hypertrophy. A strength workout is going to support your mitochondrial function in a way that supports the strength. And you don't want to think about exercise as just endurance versus hypertrophy or strength. You also want to think of cognitive exercise. So exercise your brain with memorization tasks, solving puzzles, synthesis, reading, creativity, responding to questions with answers. Whatever you can exercise about your brain function, focus on the things that help you get your goals, but also focus on making sure you're not losing weak spots. You might not care about not being able to memorize a long string of numbers when you're 25, but you might care about not being able to remember anything when you're 75. So do some exercise with memorization tasks. When you're thinking about physical activities, you want to think very broadly about all the different functions that you could have. So exercise to maintain optimal body composition, but exercise also to maintain endurance. Exercise for quickness, exercise for power, exercise for balance, exercise for proprioception, meaning perceiving your body's arrangement in three-dimensional space, but also exercise for exteroception, which means being able to perceive things outside of you. Playing a sport with someone else where you're required to respond to the external environment, even if it's catching a frisbee, is training your ability to have quick reaction time to the things outside of you. But doing a sport where you have to practice your agility and your balance and your movement, maybe dance, for example, is going to be very good at exercising your proprioception, your own perception of the space that your body occupies. And all of those things should go into your exercise routine because they're all going to stimulate mitochondrial function in different ways that are specific to the demands that you're placing on it. You don't want, you might not care about whether you can do the drills that boxers or football players would do to, move their feet very quickly when you're 25, but you might care if you're kind of losing your balance when you're just trying to walk to the kitchen when you're 75. So make sure you're exercising agility, balance, power, speed, strength, endurance, body composition, all of those things. And you're always making sure that you're preserving those capacities of your body. You're either going to use it or you're going to lose it. You need to eat a well-rounded and nutritious diet. All of the nutrients are needed for your mitochondrial function. There are different ways to do that, and there are different paths towards a nutrient-dense diet. Eating mostly unprocessed and minimally processed food cooked at home is certainly a good rule of thumb. diversity within what you tolerate and are willing to eat is certainly a good rule of thumb. But I recommend just doing a check on whether you're actually hitting your nutrient targets using an app called Chronometer. You don't have to track your diet every day forever, but track it for a few days or whatever you need to get a representative sample, and just look at your micronutrient report and see if you're meeting all the targets. You might think I eat healthy, but that doesn't mean you're getting enough riboflavin, for example. So try to eat a well-rounded, nutrient-dense diet, but also check and see if your diet is actually well-rounded and nutrient-dense. And if you're missing anything and you can't find a way to eat a food that will get it, use a multivitamin or use a targeted supplement, but always make sure you're trying to hit your targets from food first before you rely on supplements. And then fifth, I would say find a way to accentuate your fasting feeding cycle. I'm not saying that everyone needs to do 3-day, 5-day, 7-day water fasts, and I'm not saying everyone needs to do a 1 meal a day. And I don't really think there's solid evidence about what fasting feeding cycle is the best. But it does mean that you shouldn't be snacking all the time, and you shouldn't wake up in the morning and immediately need to eat before you can do anything at all. And so some ways, a very mild way to accentuate the fasting feeding cycle is do some exercises in the morning that put demands on your mitochondria before you've had a chance to eat, and really set into that fasting state. And then you can reward yourself after that. Well, there are things that everyone needs to be doing for their mitochondrial health, and there are things that we should all make sure we're doing. There is also going to be, for each one of us, a layer of idiosyncratic, highly unique individual needs based on our genetics, as well as everything up to now that we've experienced in life, whether it's things that happened to us, challenges we faced, or how we've treated ourselves in the past. And that's going to produce things that are unique, that I need to do for my mitochondria that you don't need to do for yours. And you're going to have things that you need to do for your mitochondria that I don't need to do for mine. And understanding where that is where Mitome comes in. Mitome, again, is a quick and easy cheek swab. You put it in a prepaid mailer, send it back, and within a few weeks, you're going to have your individualized results.
Mitome is not intended for the diagnosis or treatment of disease, but is rather meant to help you optimize your mitochondrial function to support maximum wellness, performance, and longevity.
The value is in knowing what you can do uniquely, and it is initial investment, but it can save you a lot of time and a lot of money on the back end, because we can waste years or even thousands of dollars, whether it's through testing or through supplements we don't need, chasing down rabbit holes and false leads, trying to trial and error our way into optimal health. And while there are plenty of things that we could all be doing better that are generalizable across all of us, and we do need to take responsibility for that, actually testing and knowing what is unique to your mitochondria can save you a lot of future waste by optimizing the cellular energy production you have starting now in this moment and carrying it forward to make the most out of each moment that you have. And for that, you can get started at mito.me.